Our last topic for this chapter will be Le Chatelier's principle. All right? The benefit of Le Chatelier's principle is that it allows us to predict the effects of changing things like concentration or temperature or pressure on a system in equilibrium. So changing some of those things can affect where our equilibrium position is and how our reaction will shift in response to those changes. All right? Now, Le Chatelier's principle says that an equilibrium position will shift to reduce the effects of a change on a system. All right? Now, first one that I'd like to talk about is what happens when we change our concentration in an equilibrium reaction. Let's say that we have the reaction at equilibrium, N2 plus 3H2, that's in equilibrium with 2NH3. All right, I've already balanced it for you. Now, what happens if we add 1.01 moles of N2 to this system at equilibrium? All right, well, you can kind of think of it like a football team, right? Let's say that we have N2 plus 3H2, and it's in equilibrium with 2H3, right? Now, the way equilibrium works is that you have two teams, okay? You've got UTM over here, and you've got a whole bunch of other teams over here, all right? Be any team you want, right? Now, let's say that UTM, right, the N2 plus the 3H2, right? We've got several players over here. Let's say that we add, right, and now, right now they're equally matched, but let's say that we add extra N2, right? Let's say we put a player on this side, right? We add a player to this team. If we add more N2, that means that this team is now stronger and it's going to push our system to the right, right? Our ball is going to advance toward this end zone, okay? So if we add a player to this side, our equilibrium is going to shift to that side, all right? That means that if we add N2, we actually end up producing more of our NH3, okay? Right now, what happens if we were to somehow remove some of our H2? Well, if we removed a player from the game, that would make this team weaker, right? So if that team were weaker, then that would mean that this team could push the ball that way. So if we remove a component, right? If we remove a molecule, that means it's going to shift toward that direction, okay? Because that side is weaker, all right? So if we removed H2, that would mean that our equilibrium would shift to the left, and we would actually produce more H2 and more N2. Okay, does that sort of make sense? All right. Now, what happens if we add some ammonia? Let's say that we add some more NH3 to our equilibrium system. Okay, well, if we added a player to this side, then that would make this side stronger, and it would shift to the left. All right, so when you're looking at an equilibrium type problem with concentration, the first thing that you're going to do is you're going to say, what changed? All right, you can ask yourself, which team gained or lost a player? Okay, the next thing that you're going to do is you're going to say, which side is stronger? Which side is stronger? Right? And then based on which side is stronger, so what changed, which side is stronger, your third step is going to be to say, which way does it shift? Right? Which way does the ball move? Right? And then your last step is what increased? Increased or decreased at the very end, right? So for instance, when we added the NH3, initially we added NH3, but it now has to shift back to equilibrium, right? So now our equilibrium, like, right, you know that the line that they put on the TV, right? Or where your down is, yeah? Now that has shifted because this one is stronger. So now it has shifted a little bit to the left. All right, that means that this side gains more of it, right? Because once we've shifted this way, we had to make more of those in order to rebalance the equilibrium. Okay, so when we increased our NH3, it shifted our equilibrium to the left. When it shifted it to the left, those went up. Okay? All right, so those are going to be your steps to determine which way it shifts. Okay, now that was what happened when we changed concentration. Right? In addition to concentration, we can also change pressure. All right? So, switching over to slide 25. Okay, we're going to look at Le Chatelier's principal effects related to pressure. All right, now there are three ways we can get effects by changing the pressure. Okay, the very first way is we add or remove a gaseous reactant or product. Okay, in this case, it shifts to alleviate the stress that we created, okay, just like the football game, okay? And then the second one, right, would be if we add, so this would be like if it participated in the reaction, right? We know that a reactant or a product, they participate in the reaction, okay? Another thing that we could do is we could add an inert gas. So a non-reactive gas. Okay, now, if we add a gas that's not involved in the reaction, okay, we'll talk about how that can affect it. The third type is that we change the volume of the container. You're like, okay, well, we're talking about pressure and now you're talking about volume. I'll explain what I mean by that in a second, okay? So, for volume, this would be like when the volume of a gas container gets smaller, the system shifts to reduce the number of molecules. Okay, so let's say that we were looking at adding or removing a gaseous reactant. All right, so that would be like, say that we had the reaction N2 gas plus 3H2 gas in equilibrium with, do a better job, in equilibrium with 2NH3 gas, right? That reaction we just looked at. Okay, let's say that we have this reaction. We know that if we add or remove a reactant, it's going to shift to alleviate the stress. So just like what we talked about last time, if we reduce one of the components, right? Like let's say we took out some N2. Well, if we take out some N2, which side is weaker? This side is weaker. So if this team is weaker, we're going to shift to the left. All right, again, ask yourself those systematic questions, okay? What changed? Which team is weaker? Which way does it shift? Okay, now if it shifts to the left, right, because that team was weaker, so it's going to shift to the left. If it shifts to the left, what increases? The N2 and the H2 are going to increase. So even though we pulled some of that out, these are going to be the things that have to increase in order for us to reestablish the equilibrium. Okay? Now, the next thing is if we add an inert gas or a non-reactive gas. Well, things that are noble gases, right, like neon, argon, krypton, xenon, helium, right, they're not going to react. They're not going to burn. They're not going to do any of that. So let's say that we added neon to our reaction. Okay, so we've got neon, and we're adding it to our overall reaction container. Okay, if we added neon, okay, and it doesn't appear in that reaction, okay, then what happens? Huh? Right? It doesn't participate, okay? It's like that friend, you know, that you invite over to the party and they sit over in the corner, right, and they count nickels in a jar or something weird, okay? So, they don't participate, right? So if I added neon, it's non-reactive, it doesn't participate, so there is not going to be a significant shift, okay? Now, if I added neon in a large amount, right? If I added neon in a large enough amount that it changed the pressure, like I increased the pressure, okay? If I increase the pressure so much, like I've added so much neon, right, that it takes up a large amount of space, then that means that the reaction will shift in order to allow for the lowest number of molecules. Okay, so what you're going to do is you're going to count the number of molecules on the left. I've got 1, 1, 2, 3, so that is 4. 3 plus 1 is 4. Over here, I have 2 molecules, okay, because I've got 2 of my NH3 molecules. That means that if I increase the pressure, the way that this ends up shifting is going to shift in the direction that gives me the fewest number of molecules. So if I add a lot of neon, it's actually going to shift to the right because it wants to have the smallest number of molecules in that container. Okay? So if I increase the pressure, then I'm going to shift to the side with the fewest molecules. Okay? That means that if I decrease the pressure, I'm going to shift to the side with the most molecules. Okay? So, if I removed a whole bunch of neon, that means that it would shift back to the side with more molecules. Okay? Now, the last one that I want to talk about is changing the volume of the container. Okay? And it sort of is the opposite of this effect, right? If we increased the pressure, if we packed in a whole bunch of people into the room, right? Then that means that eventually people are going to cluster up with their friends, right? So they'll shrink into little friend groups, okay? Because you don't want to be all nestled up against a whole bunch of people you don't like, right? Same thing with molecules, okay? They want to go into groups that they like, okay? Now, if I decrease the pressure, they go back and they all spread out to be more comfortable, right? Well, if I increase the pressure, okay, that's like the same thing as decreasing my volume, right? So if I increase my volume, right? If I made this room a whole lot bigger, right? Then that would give me more room to fit more molecules, right? So if I increase the volume, then that means that I'm going to increase, or rather shift, to the side with the most molecules. Okay? So it's the opposite effect of pressure, right? If I made my room bigger, if I made the volume bigger, then that means I'm going to shift to the side with the most molecules because I've got more room for more molecules. Okay? Now, if I made my room smaller, then that means that I have to fit the same number of atoms in the same space. So that means I want fewer molecules. Okay? So decreasing the volume means that I'm going to want to have fewer molecules. Okay? All right. So that covers our 3 different pressure shifts. Don't worry, you still have questions you can always ask in the discussions. All right, now, the next thing that I want to talk about is Le Chatelier's effect caused by temperature changes. All right, now, temperature changes the equilibrium constant. Okay. All right. And the way that it does that is, let's say that we have that reaction. All right. Excuse me. All right. We have this reaction. Now, this reaction requires heat to go to the right. So that means it's an endothermic reaction. Okay? This is endothermic. Okay? Now, if it's endothermic, that means that we add heat. That little triangle with a line in it is heat. So if it's endothermic, we add heat. Okay? So if we add heat, that means it gets added to the left. Okay? That means that this side gained a player, right? So our reactants gain a player. Okay? Which means that we shift to the right. Okay? When we add more heat. Okay? So we have heat as a player in this. So if I add heat to this, okay, which team is stronger? Well, that would make the left side stronger. So which way is it going to shift? Since the left side is stronger, it's going to shift to the right, which means we make more of the NH3. Okay? Now, this reaction is always going to be endothermic. So that means that we always have the heat on the left. Okay? We talked about adding the heat, but what happens if we remove the heat? Well, even though we're removing heat, it's still an endothermic reaction. So the heat is still on this side, right? Again, it's just like football, right? If our player plays for UTM, he doesn't suddenly switch over to be on the other team, right? He's still on our team. But if we pull him out, right, then that makes our team weaker, okay? Now, so if I remove heat from an endothermic reaction, that makes the reactant side weaker, and we shift to the left and make more of the N2 and the H2, okay? So again, you kind of have to think about that. Now, what if we had an exothermic reaction? Right, like let's say that we had I'll just do this. Let's say we have A plus B in equilibrium with C and D. Okay, now if it's an exothermic reaction, that means that we remove heat, okay? So we add heat to reactants. Here, for an exothermic, we add heat to products, or rather, I should probably say this differently. We don't add the heat, but heat is a reactant, right? We need it to react. It's a component that we add, right? It's like a recipe, okay? And if it's exothermic, then heat is a product. That's probably a better way to say it. Okay, so we have exothermic, making heat a product. So heat goes on the right-hand side. Heat plays for our other team. Okay, now if I add heat to an exothermic reaction, which team is stronger? The right-hand side, right? So that means that our equilibrium will shift to the left and we will produce more A and B. All right, now what happens if I remove heat from an exothermic reaction? Well, that means that this team will be weaker and it will pull us to the right, okay? And we will produce more of C and D, okay? So those are going to be how heat affects our Le Chatelier's principle and our equilibrium, okay? All right. Now, that would be how temperature affects it. Okay, so let's do a few examples. We're going to shift over to slide 27. All right. Now, on slide 27, we've got a couple of examples, right? So let's consider the following exothermic reaction. Okay, and our reaction is, write that a little bigger. It is C2H4 gas plus Cl2 gas in equilibrium with C2H4Cl2 gas. All right. So, if that's our reaction and it's exothermic, which side has the heat? If it's exothermic, that means that heat is a product, right? So if heat's a product, we add it to the right, okay? Now, let's answer a couple questions. Which way will the reaction shift if A, we increase the volume? Well, if we increase the volume, we need to know how many are on each side. Okay, well, we've got one CH4, we've got one Cl2, and we've got one C2H4, all right? Heat doesn't take up any space, okay, so we're not worried about that. So we have two molecules on the left, right? Two molecules on the left, and we have one molecule on the right. Okay? So if we increase the volume, that means we have more space. All right, down more space. Okay, and if we have more space, right, that means that we will have more room for molecules. So that means shift to more molecules, right, which is to the left, right, or to reactants. Okay, so that's part A. Now, then the next one, what if we remove a little bit of C2H2Cl2? Well, if we remove that, right, remember that this player goes down, right? And so which side is weaker? Right? Or you could think about it as which side is stronger, right? Always draw your line. If this side loses a player, which side is weaker? That side. So that means it's going to shift to the right. Or to products. Okay? Now, what about C? Well, for C, what if we add Cl2? Well, if we're adding Cl2, what happens? What changes? The Cl2 increases, so that side is stronger, which means that it will shift to the right. Or to products. All right, which means that we will be increasing our concentration of C2H4Cl2. Okay. D, what if we lower the temperature? Well, if we lower the temperature, what changes? It's like we're removing some heat, right? So that player goes out of play. This side is weaker. We shift to the right. Or to products. Okay, now notice that as I'm going through each of these different ones, I'm saying, okay, well, what's changing in my reaction? What player am I pulling out? What player am I putting in? Okay, and then based on which one I added, which side is stronger, so which way is it going to go? Okay, that's my entire thought process as I work through these. Okay, now, what about E? All right, what if we add carbon solid? Okay, so we're adding solid carbon. All right, now, solid carbon isn't, right, like if I had solid carbon, okay, that's going to take up a whole lot less space than if I turned carbon into a gas, right? Gases fill the space. They have a much larger volume, right? Well, if I had carbon solid, that's not really affecting my volume. It's not really affecting my pressure a whole lot, okay? So if I add carbon solid, okay, does carbon solid change my pressure? No. Does it change my volume? No, not really, okay? Does it participate in the reaction in any way? No. Okay, so that means that since it didn't really affect any of these, right, it wasn't in play, right, and it didn't affect, right, our pressure or our volume, then that means there's no shift. Okay, now, what if I added a lot of neon gas? Okay, remember neon's going to be inert. Or let's try xenon, right? Xenon is also inert. Okay. So if I added xenon, xenon's inert, right, and I add a bunch of it, okay, remember, we have 2 molecules here, we have 1 molecule here, right, because if I'm adding a lot of gas, what's happening to my pressure? My pressure's going up, okay? So if I add a lot of the gas, my pressure goes up. If my pressure goes up, then that means that I'm going to shift to reduce the number of molecules that I have. Okay, so that means the number of molecules goes down. Okay, and if the number of molecules goes down, that means that this side is more favorable and it will shift to the right. All right, or to products. Now, that concludes everything that we have from chapter 13. All right. Good luck as you study for the quiz, and I hope you guys do great.